Hello and welcome to this PLASTICE training session. In this video we will cover Module 1, Innovative Technologies to Enable Circular Plastic Value Chains, starting with Unit 1.1, Microwave-Assisted Thermochemical Processing, Prospects and Scalability. The purpose of this module is to showcase the problematic of mixed polyolefin recycling. But before going into technical details, let me introduce myself. I am Ignacio Julián, Technology Project Manager at CIRCE Technology Center in Spain and head of the Microwave-Assisted Process Development at the Industrial Recycling Technologies Division at CIRCE. My role within PLASTICE projects is to lead the technical development of innovative solutions for the thermochemical valorization of unsortable polyolefin waste, including both microwave-assisted pyrolysis and hydrothermal liquefaction. I hold a PhD in chemical engineering since 2015, and my research interests entail not only microwave-assisted thermochemical processing and solid waste recycling, but also the design and engineering of advanced chemical reactors, as well as industrial process electrification and decarbonization. Let me now give a brief overview on the tackled problem. Polyolefins represent the highest fraction of plastic waste in the yellow bin, ranging from polyethylene, polypropylene, polystyrene, or PET. In case they could be fully isolated, they could be individually recycled by thermochemical treatment. However, reality is more complex than that. Plastics in the yellow bin appear fully mixed, being the overall composition and even among waste plastic bales. Furthermore, the separation is troublesome due to small discrepancies between both physical and chemical properties among plastic types. As such, sorting by means of density, shape, or physical appearance do not solve the issue, and polyolefins waste mixture cannot be fully isolated. To overcome this limitation, chemical recycling comes into play. The purpose is to treat the bulk plastics fraction thermally at temperatures that are high enough to break plastic polymer chains into smaller hydrocarbon fractions that can serve as building blocks for the construction of second-generation plastics. The pool of hydrocarbon molecules resulting from the thermal breaking of the polymer represent the so-called pyrolysis oil. In our project, we aim to cover the full value chain of plastics recycling, starting from the recovery of plastic from the yellow bin, the sorting of polyolefins, the pretreatment of the plastic mixture to be recycled, the thermochemical recycle process, and the upgrade of the obtained products through catalytic cracking and repolymerization towards the production of second-generation polyethylene. Within the process flow, our main innovations lay in the sorting and in the agglomeration mechanisms and the thermochemical recycling process through unconventional pyrolysis procedures. Regarding the thermochemical recycling process, which is the core activity along the overall process, this is typically a very demanding system in terms of energy consumption, and it's hindered by a low control on oil's quality derived from the uneven plastics decomposition due to the heat transfer limitations. What we propose to overcome these limitations is the so-called microwave-assisted plastics pyrolysis process. What is meant by polymer pyrolysis? I already mentioned that the polymer is a long chemical structure composed by small concatenated units or monomers. These units consist of many hydrocarbons, that is, combined carbon and hydrogen atoms, eventually combined with some heteroatoms such as oxygen, nitrogen, or chlorine, as for instance the PVC molecule shown here. Pyrolysis consists in heating these polymers in the absence of oxygen, that is, avoiding the combustion and formation of flames, up to a temperature that promotes chemical bond breaking. Depending on the nature and strength of these chemical bonds, as well as on the process temperature, the polymer scission and chain recombination keeps evolving until the temperature is cold enough to stop promoting such chemical reactions. This concept of temperature-driven reactions is the key to understand the potentials and prospects of microwave-assisted pyrolysis. Microwaves are just a small region of the radio frequency band involving electromagnetic waves with wavelengths ranging from 1 meter to 1 millimeter. These electromagnetic waves have the ability to change the polarity of the irradiated polar substances, shifting the dipolar moments of their molecules from positive to negative and vice versa. You all have heated up your meals in a conventional microwave oven at home in some seconds. The heating principle there lays in the dipolar moment shifting of water molecules within the food. The standard frequency of microwave ovens at home is 2.45 GHz. This means that your water molecules are turning upside down 2.45 million times per second. This molecular rotation generates friction at a nanoscale, thus leading to energy loss in the form of heat. This effective way to lead electromagnetic power into materials heating is deemed responsible of the superior performance of thermochemical processes assisted by microwaves. As it can be observed, the heating rates are maximized. Consequently, the heating times are strongly reduced, and so the overall polymer degradation time. Moreover, microwave heating is selective since the gaseous non-polar surrounding environment of the targeting irradiated solid material doesn't become heated at all and thus remains much colder than the irradiated sample. And this represents the key advantage of such a heating system. The randomization and recombination of hydrocarbon chains are produced upon plastics pyrolysis in the gas phase beyond the sample and can be controlled and quenched or stopped on demand thanks to the large temperature gradient induced between the heated sample and the surrounding comparatively cooler atmosphere. Besides, energy losses by convection and diffusion are strongly minimized, making microwave-assisted heating more energy efficient. Moreover, derived from previously mentioned heating mechanism characteristics, the microwave-assisted heating processes lead to drastically faster startup and shutdown times. All these concepts and prospects were evaluated for the targeting polyolefin mixture pyrolysis process. Here I show you our bench-scale experimental setup devoted to the technology validation. It consists of a multi-mode microwave oven working at 2.45 GHz, as already said, similar to yours at home, featured by a tubular reactor containing a mixture of plastic waste and microwave susceptor particles to boost sample heating and the volumetric thermal homogeneity. Once pyrolysis temperatures are reached, the organic vapors containing polymer fragments or hydrocarbon chains are driven through a condensing system for condensation and pyrolysis oils recovery. And what we observe in our experimental trials? Very relevant things indeed. First, under conventionally driven pyrolysis, namely using electrical heating resistances or fuel combustion as heating source, the pyrolysis oils contain linear aromatics molecules being the linear fraction composed by alkanes and monoalkanes. On one hand, aromatics are undesired feedstock for the repolymerization process, aiming to get second-generation polyethylene. On the other hand, alkenes, also called olefins, which are the building blocks of polyolefins, appear in lower proportion with respect to alkanes, or also called paraffins. In contrast, microwave-assisted pyrolysis oils reveal a drastically different composition. First, they are aromatics-free. Second, the alkene-to-alkane production is completely twisted, boosting the presence of the olefins. And third, terminal dienes are systematically found. These compounds, that are also of interest for the production of second-generation polyolefins, are pyrolysis reaction intermediates. And this showcases what we wanted to validate, the thermal gradient between the irradiated sample and the surrounding environment acts as chemical reaction stopper so as to get the desired oil composition on demand. Once we validated the proof of concept our next step was to optimize the pyrolysis process to maximize the production of pyrolysis oil against gas and carbonaceous solid byproducts. Three process variables, such operating temperature, susceptor to plastic waste ratio, and sweep gas flow, were simultaneously evaluated to assess the combined impact into oil's production. In order to speed up the optimization process, a predictive model was created to minimize the experimental workload towards the selection of the most appropriate operating conditions. The robustness of the tool allowed us to predict the oil yield for a combination of operating parameters with less than 10% error. This predictive model represents a key feature to proceed with the scaling of the microwave-assisted pyrolysis process to a continuous pilot plant. To sum up, here you can find the key learnings of this module. First, mixed polyolefin plastic waste is difficult to be recycled due to its complex composition and sorting. Second, the valorization of this waste via pyrolysis to produce oils that can be used for the production of second-generation plastics is the most eco-friendly management route. Third, microwave-assisted pyrolysis enhances the control over the oil product's distribution, minimizing the energy consumption of the process. Fourth, the sort of oil product is more interesting than those obtained under conventional pyrolysis, especially due to the fact that the generation of aromatic compounds in the oil is completely avoided. And fifth, the process could be optimized to maximize oil yield by evaluating different experimental pyrolysis operating conditions and using a home-developed predictive model to assess the most appropriate conditions to boost transformation of plastics into oils. And with these remarks, I conclude Unit 1.1. So coming up next in Module 1 is the gasification and catalytic post-treatment for circular plastic valorization of syngas to olefins conversion. Thank you for watching this training video. Stay tuned for the next units, where we will continue exploring innovative technologies for circular plastic value chains. Thank you.